Hello everyone, this is Andrea from Hello Academy and Brain Boosters, and today we are going to see the concurrency. Okay, this is chapter 26 of operating systems, 3 easy pieces. So let's get into it. So the concept of thread, this is a new abstraction for a single running process, and we have multi-threaded processes as well, multi-threaded programs. So in the multi-threaded programs, as you know, in the program we have a process, then the simple unit of process is thread. Just you can see like that. Okay, so the multi-threaded program has more than one point of execution, because it cannot it has multi point of execution and multiple pieces or program counters. It has multiple pieces and program counters, and they share the same address space. The issue is they have the same address space. So this is the behavior of multi-threaded program. And context switch between threads, it's expected, as you know. So each thread has its own program counter and set of registers. One or more thread counter blocks are needed to store the state of each thread. In the time of context switch, thread counter block will be used. When switching from running one thread 1 to running to other thread 2, so what it does is the register state of T1 will be saved, this is obvious, and the register state of T2 restored. Then the address space remains the same. This is the behavior for the context switch between threads. And as you can see, the stack of the relevant threads, thread will be one stack per thread. If it is a single threaded address, as you know, we have this address space and we have the stack, we have thread, this is the heap and this is the program counter. So the core segment where instructions lives, and the heap segment contains malloc. This we have seen in our previous chapters, dynamic data structure. It grows downward, and we have stack segment contains local variables, arguments to routines, and return values etc, and it will grow upward. So this is 16 kilobyte, and this is single threaded. But when it is two threads, as you can see, we have the stack 1 and stack 2. So each thread will have its own stack. That is the behavior of multi-threaded. So why to use thread? What is the benefit of thread? The first one is parallelism. This is speeds up computations. And the second one is avoid blockage. Blocking a process progress due to a slow input-output process enables the overlap of input-output and computations within a process. Example, like spell checking using a background thread in a word processor. These are some of the examples. So this is thread creation example. This is I took it directly from the book, and as you know, I'm just giving you this lecture from the book, so I encourage you to read the book also for more detail. But this is the thread creation example. This is the stereo H, include this old. Then we have my thread. This is the my thread, and we have void, argument, then print. And as you can see, we have int, and the main in the main we have int, arg, and we have the character. Then as you can see, p thread is going to have p1 and p2. And if you go and see here, what it does is p thread create p1 it will print A, and for P2 my thread will print B. Okay, this is the main. Always we have main thread here, and we have 2, 3. So in this case we have 3 threads. Okay, the main and P1 and P2. A and B will be printed. Then in the join waits for the thread to finish. That means P1 will run, okay, then P2 will continue, then the main will continue. That's how it runs. So you can download the code T0C and T1C. It is already in the website, and let me demonstrate that. Okay, let me demonstrate that. Go to your Linux. Okay, this is our Unix, so let me make this here. Okay, so what we are going to do, let me open the terminal here. So let's see the files. As you can see, this is our file T0C, T1C, and if you want to see the T0.c file, this is the code. So we have include and everything. We have the my thread, and we have the main function. Okay, and this is a creation P1 and P2. It will print A and B, and we have also the wait function for P1, P2, and the main function. So that is what it does. So let's execute it. Okay, sorry. So what we have to do is TO. Okay. What are the weights? Sorry. Okay, so what we have to do, T0. Okay, so as you can see, it's already, I compiled it already. That's what, nothing to be done for. And as you can see here, the main, now even if our code says first print A, but now the scheduler is choosing B. Okay, and let's continue again. T0 again, B0. Okay, T0. Now as you can see, now it is A, so main A, B. Now it changes. So the scheduler, it depends on the scheduler. The execution will be depend on the threads which will be scheduled. So this is something, the concurrency. In our concurrency, that is one thing. So it has a lot of paths for execution. So this is the first demonstration which I want you to know. So as you can see, A, B, but here B, A. So let's go to our presentation and let's continue. So as per the recommendation of this book, the possible execution of path 1, for example, as we have seen, the first one is BA, BA, then the last one was AB. So as per this thread creation example, possible execution for path 1, for example, the main function start running, print main begin, then creates thread 1 and create thread 2, then wait for T1. Then when the thread 1 was chosen, it runs print A. this return. After that, wait for T2. After that, it will run print B2, then print main int. This is the first pass. The second possible pass could be start running, print main, then create thread 1, then run print A return, then automatically creates thread 2. Okay, then what it does will be runs and print B. After that, wait for T1. Then because T1 already is run here, so immediately T1 is done. Again, wait for T2, then return immediately T2 is done already because it's already run. Then print main and int. This is the thread trace for the pass 2. Okay, this is a possible pass 2. And the third one, thread execution, possible execution pass 3 will be start running, print main, then create thread 1 and create thread 2. Already T1 and T2 is created here. Then automatically runs the scheduler will choose B, then runs B will be printed, then wait for T1, then run, then print A, then wait for T2, but already B is complete, T2 is complete, then return immediately T2, then print main int. This will be the third possible execution. So what is the reason for so many possible execution paths? This is only scheduler. Okay, it is because of depend on the thread scheduler. That is the answer. Now let's discuss about shared data example. And in the shared data example, this is the code also. I took it from the book. You can directly download it also. We're gonna see it together. And in the shared data, this is a simple code. You can go and see, for example, simply this is my thread, a static volatile int counter. The counter starts from 0. Then my thread, simply add 1 to the counter repeatedly in the loop. And this is not how you would add. For example, we're gonna start with 10 million, okay, to a counter, but it shows the problem nicely. We're gonna see that, okay. So what we are going to do, void, this is my thread, this is the main, then print, then this is the counter. Okay, the counter, what it does is the counter is simply adding 1, and this one we will cover because what it does under the hood is this counter in the critical section problem. We're gonna see how this counter, when it goes from 1 to the next incrementally, first it will move, okay, it will move any data which is in this counter into a register AX, then it will add 1 into it, okay, it will add into any value in the AX, then it will move the value the same AX into the same register, the register which is the same 8049A1C. This is the register, okay. So the main function is just launch 2 threads, okay, pthread creates and then wait for them, then pthread joined int main function. As you can see, pthread P1 and P2 is created here, and pthread created P1 and it will print A, P2 will be print B, and join, wait for the thread to finish, and we have pthread joined P1 P2, then the main will be done with both counter, then return there. This is the shared. We will come here what after the demonstration. Again, let's go and demonstrate this instead of theory. Let me, okay, so this is our Linux. This is our Linux. Okay, Okay, so what we are going to do, let me open the as usual, and our files are here. So now we need T1. Okay, if you want to see T1, T1.c, this is our code, the same code. Okay, the same code. So let's quit. And what we are going to do, I think it's already okay. So what we are going to do, T1, okay, T1. Okay, now I'm going to give it T1 100. Okay, that means our first thread will increment it by 100, and our second thread will increment it by 100. So the result should be 200. Okay, so as you can see here, our code is doing great. The main began. Okay, this is the register, this is the stack. So the address of the stack is here. So B begins, B done, then A begins, and A done, then main done. So the counter is 200 and it should be 200. Now no problem until now. Now let's make it like let's give T1 like 1 2 3 4 5 6 7. So let's increment it like 1 2 3 4 5 6 7. Let's see. As you can see, automatically the main begins, then A comes, then B, then A, then B, then the main, then the counter is wrong, you see, because it should be 20 million. Okay, it should be 20 million because we give 10 million, but the counter is here. Okay, again we can increment by like the same. For example, T1 1 2 3 4 5 6 7. Again, you see, we have another, the counter gives even A, B, and the counter gives us another number, and this one is 20 million. It should be 20 million. If we give again the same 1 2 3 4 5 6 7, you see, it gives us another value. Finally, let's see, show you 3 4 5 6 7, the same another value, you see. So this is the problem of concurrency, because why this happen, why the counter is giving us different values here. It should be 20 million, but it's giving us different values. So why is that? What is the issue? This is the question we have to answer. Yes, so why this discrepancy happened? It is because of scheduling. Of course, it's because of the scheduler, but why is that? It is because of the critical section problem. Okay, the critical section problem. So what is the critical section problem? Here in the shared memory, the critical section, when the counter increment by 1, when we the very important note on this case is that in the example code we have a critical section here. In our programming language we have counter, and we have the code to increment the counter. This code, if it is compiled and see the assembly code, then it will be 3 instructions. This is the assembly code 1 2 3. So the first one is move whatever is in the counter, okay, to EAX register. So whatever is in that counter, because the counter starts from 0, and it will move into AX register, then add 1, okay, whatever is in the AX register, add 1, then move EAX to the address of the incremented counter. That is what it does, okay? However, since we have different execution paths, as we have seen there, as we have seen here, execution path 1, path 2, path 3, we're gonna have a lot of paths. So because of that, it is possible that during trade context switch, some operations might be missed off, resulting in incorrect result. So that is the main issue of the critical section, okay? And it has different paths for the trades executed, then that will create a problem. So as you can see here B was first, then here A comes, then again the counter, we gave it 10 million, we expect 20 million, but the counter gives us different execution because of these three assembly, as we have seen in the counter, the assembly register and the paths. Because of that, that is the issue. So just race condition, that is the race condition. The result depends on the execution path because we have different paths. Example with two trades, okay? Trade 1 and trade 2. The counter is counter plus 1. This is default. Let's make it 50 first. Then we expect the result 52. We have seen in the Linux now in the code very nicely, but just to demonstrate for you. But we have trade 1 and we have trade 2 here. So let's start from trade 1. So program counter and start with 100, and the counter is 50 here. Then after instruction, as you see, the move will take 5 bytes and the add will take 3 bytes. And the move, the program counter 50, then when it takes to add, it comes to 51. Then when in this condition 51 interrupt happen, then save this state, T1 state will be saved and restore T2 to the state. So this will be T2. So as you can see, 100, 105, 108 is the same. Then 5 will be added for the move, 5 byte, and this one is 50 and 51. So as you can see in the move, the counter is 51, no change. Then again interrupt happen, then save T2 state, restore T1 state. So in the T1 state 113, 51. So the result will be, as you can see, is 51, but we are expecting 52. So this is the race condition. Critical section, as we have seen now, a piece of code that access a shared variable and must not be concurrently executed by more than one thread, because executing it might result to a race condition and generate an incorrect result. This is the very famous problem in the critical section problems. So solution need to support atomicity. All instruction execution in the critical section will not be preempted. This is the first. For critical section, access mutual execution should be applied. Multiple threads executing critical section can result in a race condition again, and need to support atomicity for critical section. This mutual execution, as we have seen, will need a special hardware instruction and operating support, okay, OS support. So the lock, this is one of the thing. Another abstraction that a thread will not be able to execute in the critical section unless it holds a lock. So ensure that any such critical section executes as if it were a single atomic instruction. Execute a series of instructions atomically, like this mutex X, lock T and lock. So balance +1, then unlock mutex. This for the critical section, you can use this kind of code. So condition variables, some problem will require waiting for another thread. This is synchronization. So threads for IO processing. Other synchronization problem, we have bounded buffer, producer, consumer, readers, writer, diner, dining philosopher problems, and so on. So in the nutshell, this was chapter 26, and we have seen logs, critical sections, and we see race condition, and we have seen the codes. Even you can download it and you can play around, and we have seen what it should be, the counter, and but the exact counter, why this happens and why the discrepancy happens. It is because of scheduling. And the critical section problem we have seen here because of the move, add, and again move commands. This is the assembly code of our simple code, and because of this some operations might be missed. Because of this the problem happened. And what is the reason for so many possible execution paths? We have seen the scheduler problem, and we can have a lot of paths for the thread, and we have seen also demonstrated the Unix code here, and you can download the codes, and this is simple codes for how threads are created. And we have seen why you use the benefit of threads, and we have seen also the single thread address space and the two thread address space. In the two thread address space, each thread will have its own stack, and but here we have only one stack. And context switching between threads also, the mechanism. And that was the concurrency problem, and I hope this will help you to give you some idea what is concurrency and what the problem. And that was it. I encourage you to read the book and download the course and practice yourself. Thank you so much. We shall meet in the next chapter. This is Engineer Selassie from Yellow Academy Brain Boosters. Bye bye. Thank you.